All right, so I'm gonna, just like last time, I'm gonna work through some of the problems in the PDF that I sent everyone. Yeah, right now all of you should be muted. I'd prefer if you guys have a question or anything, I'd prefer if you guys post in the chat, just because if all of you try to talk at the same time, that's gonna be a little bit difficult. It could be that audio is disabled for you guys. I think that's supposed to be the case. But I think I've seen instances where somehow people are able to talk. So I'm not 100% certain about that. So yeah, I'd prefer if you guys talk through the chat instead. Okay, so I'm gonna go ahead and look at part 1 in the practice problems that I sent to all of you. So part 1 was about improper integrals. All right, so I'm gonna pick a few of these questions to work through. I think I will start with question number 3 first. Okay, so for problem number 3, we had this improper integral. It's from negative infinity to infinity. And we're integrating 3x e to the negative 6x squared dx. All right. So when you have an integral from negative infinity to infinity, the way that you're going to evaluate this is you're going to split it into 2 improper integrals. So we can split it so that we have one integral from minus infinity to 0. And then we'll plus another integral from 0 to infinity. Okay. So anytime you have an improper integral from minus infinity to infinity, you'll split it into 2 improper integrals like that. It's not that important that you use 0 for the place where you're splitting it. But 0 is usually like a really nice number to go with, so you may as well just always do it this way. Now the way this is going to work then is you have 2 improper integrals. Yes, I am recording, and I'll upload the recording to YouTube just like I did last time, and I'll send everyone a link to it as well once it's up. All right, now, when you have an improper integral from minus infinity to infinity, for such an integral to converge, you need both the improper integrals from minus infinity to 0 and the improper integral from 0 to infinity to converge. It's all in Japanese, really? Oh, yeah, but I think you probably are muted, meaning that you're not going to be able to speak through a mic. So again, please just post in the chat if you have a question or something that you want to say. All right. Okay, and then let's see here. All right. So if if even one of these improper integrals, so if even one of these improper integrals diverges, the improper integral from minus infinity to infinity also diverges, okay? So these are just some rules that are good to know for improper integrals from minus infinity to infinity. All right, now let's actually work on these two integrals that we have here. All right, so first, I'm going to just look at this indefinite integral to start with. So we're going to need to evaluate this anyways in the process of getting proper integral. So I'm just going to do this part first. All right, if I want to integrate this, I can do that by doing a substitution. So I will choose u to be the exponent, negative 6x squared. And du is going to be negative 12x dx. And I'll go ahead and divide both sides by negative 12. So I'll get negative 1 over 12 du is x dx. Okay? All right, so then in my integral, okay, so this 3 I'm going to put it outside. Here I'm going to get e to the u. Okay. The x dx together will be replaced with a negative 1 over 12 du. So I'm going to put the negative 1 over 12 outside, and then I'll put the du at the end. All right? From there, negative 3 over 12, I can simplify that to be negative 1/4. And then here, the integral of e to the u du is just going to be e to the u. All right, and then I'm just going to replace u with negative 6x squared. Okay. So right now, that gives me the indefinite integral of this function that we have. All right, and so then I want to use that to evaluate my two improper integrals over here. So let's start with the one from negative infinity to 0. And then before I continue, I'll just ask if anyone has any questions about anything that I have done so far. Okay, let me address that question after this problem. Let's see here, what happened to the x from the 3x? Are you talking about when I did the use of how, like here I have an x, but then the x disappeared over here? So we replaced the x and the dx together with the negative 1 over 12 du. So that's why it ended up disappearing. Okay. Okay, all right. Any other questions before I continue? Okay, all right. Okay, so here we're trying to evaluate this improper integral. All right. Now we've already computed the indefinite integral, or the derivative of this function. So we know it's negative 1/4 e to the negative 6x squared. And then instead of writing plus c, I want to try to like evaluate at these bounds from minus infinity to 0. All right. But since minus infinity isn't like an actual number, technically we don't really want to like evaluate like at negative infinity. So what we do instead is we rewrite it as a limit. So that's what I'm going to do here. So I'm going to write it as a limit as t approaches negative infinity. Negative 1/4 e to the negative 6x squared. And then I'm just going to do from t to 0 here. And so since t is approaching negative infinity, that's going to capture the idea of trying to evaluate at negative infinity, which is what we were trying to do here. Okay. Now it's not important that I use the letter T. You could have used really any other letter that you wanted. I just like to use the letter T, so that's what I went with. So now at this point, we'll go ahead and plug in 0 for x. So when we do that, e to the 0 is 1. And then we have to minus what we get when we plug in the lower bound. So when I plug in t for x, I'm just going to get negative 1/4 e to the negative 6 t squared. Okay. So I'll simplify a little bit. All right, so as I said, e to the 0 is 1. And here we've got a double minus, so I'll write it as plus 1/4 e to the negative 6 t squared. Okay, so finally, we want to evaluate the limit as t is approaching negative infinity. Okay, so if we were to sort of imagine plugging in negative infinity for t, okay. So since we're squaring it, it's going to become positive infinity. And then times the negative 6, whoops. That's going to make it negative in the end. And then when you have e to a power of negative infinity, that is going to be equal to 0. Okay. So you can take that to be a general rule, and just for reference, if you have e to a positive infinity, it's going to be infinity. Okay. All right, but what that means then is as t approaches negative infinity, this term should go to 0. Okay. But we still have this negative 1/4 that was at the beginning. So ultimately, we're going to get an answer of negative 1/4 for this first improper integral that we have. Okay. All right, so any questions about anything so far? All right, so that was the improper integral from negative infinity to 0. Now we also needed to do the improper integral from 0 to infinity as well. So let's just go through that one real quickly. It's going to be very similar. Okay. So from earlier, when we evaluated the indefinite integral, it was negative 1/4 e to the negative 6x squared. But this time we're going to plug in 0 and infinity. Let me see what that was. Yeah, I'm working on problem number 3 from part 1 and the practice problems that I sent you. So that was it was an improper integral from minus infinity to infinity. So we broke it up into 2 improper integrals from minus infinity to 0 and then 0 to infinity. I've already worked out this improper integral, and I'm working on the one from 0 to infinity right now. Now again, formally, when you're trying to evaluate at infinity, you want to rewrite it in terms of limit. This time I'll do the limit as t approaches infinity. Okay, sorry, my laptop froze for a little bit there. All right, so then when we plug in t for x, we're going to get negative 1/4 e to the negative 6t squared. Then we're going to minus what we get when we plug in 0. So when we plug in 0, it's going to be negative 1/4 e to the 0, and e to the 0 is just 1. So it's just going to be negative 1/4. All right, and then here, when you're trying to evaluate at infinity, so if you were to sort of plug in infinity for t, you get e to the negative 6 infinity squared. All right, so infinity squared is just infinity still. And since you're multiplying by negative 6, it becomes negative in the end. And then, as I mentioned earlier, e to the negative infinity is going to be 0. All right, so that means that in the limit, this term goes to 0. And we're just going to be left with minus negative 1/4, which will be plus 1/4 for our final answer of 1/4 for this improper integral. Okay. Then finally, going back to the original question, which was the improper integral from negative infinity to infinity. So we broke it up as the improper integral from minus infinity to 0. and thus the improper from 0 to infinity. And now we've evaluated both of these. So the one from negative infinity to 0 ended up equaling negative 1/4. The one from 0 to infinity we just found is equal to 1/4. So if we add them together, we get a final answer of 0 for the improper integral from negative infinity to infinity. Okay. All right. So any questions about that entire problem? And then I'm also going to look at number 5 next. But before that, I'll go ahead and address the question from earlier about when to use U-sub or integration by parts. But just first, any questions about this? Okay. All right, so back to earlier when I did my U substitution. So we chose U to be the exponent negative 6x squared. And then just when you were computing the derivative of negative 6x squared becomes negative 12x. Okay. All right, any other questions? All right, so in that case, I'll talk a little bit about just when to do substitution versus when to do integration by parts. And give me maybe a couple of seconds because my computer is slightly frozen at the moment. Recently, I've noticed it freezes somewhat frequently. So I don't know if that's an issue with my laptop, but just as a head up, if that happens a couple of times in my review, I will have to apologize for that. Oh, there you go. Okay. All right, so then as a quick aside, I'm talking about U substitution versus integration by parts. Okay, so when there's kind of at least when we're dealing with exponentials. So when you have the integral of some like polynomial, and then you have times an exponential, and that exponential doesn't have any higher powers of x in it. So it's just going to have just like an x with possibly a constant. For this type of integral, you're going to do integration by parts. Whereas if in the integral you have an exponential, but it has a higher power of x in it for the exponents, This type of integral, you're going to do u sub instead. Okay. And then likewise for, I'll just mention a little bit, if you have involving natural log. So if you get natural log inside the integral, so unless you've got like a 1 over the inside the integral as well. So for this type of integral, this could be done with a u substitution. But if you have a natural log, then you don't see its derivative, 1 over the inside somewhere in the integral as well. It's going to be integration by parts instead. That's sort of like a rough idea of when you should be doing u sub versus integration by parts. So just like in general, if there's a natural log, if you see its derivative in the integral as well, do a u sub. If you don't, do integration by parts, okay? Does that answer the question for you? Okay, all right. Hope that's good enough. Cool, all right. So then I'll do one more of the problems from the first part. So I'm going to take a look at problem number 5. So that was the improper integral, whoops, from 1 to infinity of the natural log of x over x squared. All right, so for this integral, I don't have the derivative of the natural log of x in the integral, at least not quite, because I have 1 over x squared rather than 1 over x. So because of that, I'm going to do integration by parts on this one instead. So for integration by parts, so we choose u to be the natural log, and then du would be 1 over x dx. No, so then dv is going to be the 1 over x squared dx that we have remaining. So remember that 1 over x squared is the same as x to the negative 2. So to get v, when we integrate this, we're going to add 1 to the exponent, and then divide by the new exponent. And then here, if I were to rewrite this, I could write it as negative 1 over x, okay? All right, so doing integration by parts. So remember the formula is u times v. Okay? And then it was minus the integral of v times du. And then let's write out the formula here as well, so that we remember it. Okay. And then from here, just simplifying a little bit. So here it's going to be minus and negative, so it's plus. And then 1 over x times 1 over x gives us 1 over squared. And now we need to evaluate the integral of 1 over x squared, which incidentally we already did over here. So rewrite it as x to the negative 2 by the power. It's going to give us negative 1 over x. Okay. All right, so for the improper integral here, okay, so we're going to get negative ln of x over x minus 1 over x. And instead of writing plus c, I want to evaluate from 1 to infinity. And formally, to evaluate at infinity, I need to write a limit. So I'll do the limit as t approaches infinity. From 1 to t. All right, and then from here, first we're going to plug in t for x. So we'll get negative natural log of t over t minus 1 over t. And then we need to subtract what we get when we plug in 1 for x. So plugging in 1, we're going to get natural log of 1 over 1 minus 1 over 1. Now remember that natural log of 1 is equal to 0. So this whole thing becomes 0. So that just leaves us with minus negative 1, which I'll simplify to be plus 1. All right, so this is what I have so far. Now, if we were to think about what happens when we plug in infinity for t. All right, so this term is easier. Let me start with this term first. If you were to plug in t for infinity, you would just get 1 over infinity. And remember that something like 1 over infinity is just going to be equal to 0. So we're really just going to get 0 when this goes to infinity. Now thinking about this other term that we have, this first term, it's a little bit more complicated. All right, but as t goes to infinity, it looks like we're going to get a negative ln of infinity over infinity. And natural log of infinity is going to be infinity as well. So we're getting this infinity over infinity situation. So as you guys may recall, when you get infinity over infinity, in order to evaluate your limit, one thing that you could do was apply L'Hopital's rule. All right, and I don't know if you guys remember what L'Hopital's rule was. So let me remind you guys over here. So L'Hopital's rule was if you have a limit as x approaches something, could be a number, could be infinity, of a function over another function. And if it's giving you a 0 over 0 or infinity over infinity, indeterminate form, then you can evaluate the limit by doing the limit of the derivative of the numerator and then over the derivative of the denominator. Oh, picture is frozen for you guys? Okay. Well, let's see here. I will go ahead and try to stop sharing briefly and then reshare, and we'll see if that works for everyone, okay? So just real quickly. All right, everyone can see what I have so far? Okay, all right. All right, so then I'm going to apply L'Hopital's rule to this limit since it gave us an infinity over infinity. So according to L'Hopital's rule, I can instead do the limit of, and then what I want to do here is take the derivative of my numerator, derivative of natural log of t, remember that was 1 over t, and now divide by the derivative of my denominator, and derivative of t is just 1. And then I'll just keep carrying this plus 1 that we had down, okay? And here, if you plug in infinity for t, so you'll get 1 over infinity. And again, a number divided by infinity is just going to be 0. So in the end, we're just going to get 0 plus 1, which means in the end, we find that our improper integral converges and it evaluates to the value of 1. Okay? All right, so then any questions about that problem? Yeah, so I can do that one pretty quickly. Any questions about this problem though before I do that one? All right then, so got a request for it. I feel like I can do it pretty quickly, so I'll go ahead and also visit problem number 1, which was the improper integral from 1 to infinity of x minus 1 all over 3x squared minus 6x plus 4, and then cubed. Okay, so then first things first is I just want to think about the indefinite integral of the function that we have, and thinking about how we would evaluate this. All right, so we can evaluate this by doing a u substitution. So I would choose u to be the inside of the parentheses here. Okay. So if we do that, then we're going to get du is getting the derivative 6x minus 6 dx. Okay. All right, so in the integral, we're going to get u cubed in the denominator. And then I noticed that we have an x minus 1 in the numerator. And notice that we can get an x minus 1 down here if we just divide both sides by 6. Okay. So then from this last equation, we see that we can replace x minus 1 dx with a 1 over 6 du. Okay. Then we still need to evaluate this integral. So for 1 over u cubed, you'll want to think of it as being u to the negative 3. So then when we apply the power rule, going to add 1 to the exponent and then divide by the new exponent. So then I'll multiply the negative 2 with the 6 in the denominator, so we're going to get positive 1/12. And then we're going to have u to the negative 2, which I'll move to my denominator. And then the last thing I'll do is just replace u with the original 3x squared minus 6x plus 4. Okay? Okay, yeah. It shouldn't be negative 1/6, so I just randomly added a negative sign for some reason. Yeah, thank you. So that means it'll be negative in the end then. Okay. All right, so then now that I've evaluated the indefinite integral, I'm just going to take my result and plug it into here. Oops. So we had the negative 1 over 12. I think I'll actually separate the negative 1/12 from everything else now. That's not really a big deal. All right, and then we want to evaluate from 1 to infinity. And remember that to evaluate at infinity, you're supposed to write it formally as a limit. So I'm going to do that next. And so then here at this point, we'll plug in t for x. I'll go ahead and pull the negative 1/12 out maybe. Though it's not a big deal, so I don't have to, but I'll go ahead and do that. And then plug in t for x. And then minus what you get when you plug in 1 for x. So when I plug in 1 for x, I'm going to get 3 minus 6 plus 4, which should leave me with 1, and then squared. All right. All right, so then this part is just going to be minus 1. As for this term here, I guess I can see why maybe it wouldn't be too clear, but as t approaches infinity, so the first term is going to be infinity, but I guess I see that it looks like you're going to get minus infinity for the second term. But I feel like it's pretty clear that since this is a higher power of t, we know that that's going to be the dominant term. So since this term is going to infinity, in the end, we can imagine getting 1 over infinity in the end in the denominator. And then remember that 1 over infinity is just going to be 0. So then for this one, looks like this improper integral will converge, and it seems to converge to an answer of 1/12. Okay. All right, but any questions about that? Okay, so with that, I'm going to move on to part 2, which was just computing some partial derivatives. And I'm just going to do a little bit from here. I'm not going to do too much because we'll have plenty of opportunities to compute partial derivatives in some of the other parts. Okay, so looking at part 2, I figured I would just take a look at part 3, or sorry, question 3, where we're given the function with the natural log in it. And this one's pretty messy, but I figured I would just compute fx, fxx, as well as xy. Okay. All right, so first, if we want to compute the partial derivative with respect to x, okay, so we have to remember how derivatives of natural logs work. So if you don't remember, when you're doing the derivative of a natural log, whatever function you have on the inside, what you do is the rule was to put the inside in the denominator, and then take the derivative of the inside, and that would go in the numerator, okay? All right, so I'm going to apply that same rule to here. So we take the inside and put it in the denominator. And then we're going to need the derivative of the inside. And here I'm doing the derivative with respect to x, okay? So when we look at the derivative of the inside with respect to x, so you'd be treating y as a constant. So here, doing the derivative of x squared, it's going to be 2xy. Y is treated as a constant, so this term is just going to go to 0. And then derivative of 3x with respect to x will be 3. All right. So then, any questions about how I got fx right now? All right, so then next, if I want to compute fxx, okay, now here I've got a function of x over a function of x. So when I'm trying to take the derivative, I'm going to need to use the quotient rule for this one. So let's recall the quotient rule. So the way that I usually remembered it was u over v prime is u prime v minus u v prime over v squared, okay? All right, so my u is the numerator, my v is the denominator. Now for the derivatives, I'm going to do everything with respect to x because I'm looking for fxx. All right, so u prime, or in this case, ux. So partial derivative of this with respect to x is just going to be 2y. Whereas partial derivative of v with respect to x is going to be 2xy plus 3, okay? All right, so I'm going to plug everything into the quotient rule now to get fxx. Ux would be the u prime, and vx was going to be v prime, okay? So I'm going to have my u prime times v I'm going to have minus u times v prime. So v prime is times another 2xy plus 3. Since I'm multiplying two of them together, I can write it as being squared. And then we're going to have v all squared. Okay, so that's going to give me my fxx. And since I'm not doing anything else with the problem, I'm not going to simplify this one too much. So I'm just going to leave it as it is, all right? All right, and then I'll just do fxy, so one more of them. Okay, so for fxy, I do have y's in both the numerator and the denominator, so I'm definitely going to have to do the rule again. Okay, so then we still had the same u and v being the numerator and denominator. Okay. But this time when I'm computing my u prime and v prime for the quotient rule, since I'm finding fxy now, I'm going to need to do the derivatives with respect to y. So partial of u with respect to y is going to be 2x. And here partial of v with respect to y is going to be x squared minus 2y and plus 0. Okay? And now we'll just plug everything into the formula for the quotient rule. Again, u prime v prime will be played by the rows of uy and vy. So we're going to have uy, which should be like our u prime, and times v. And then it's going to be minus u times v prime being our vy here. And then all over v squared. And then that gets us fxy, all right? Then I'll just also recall a fact that for any function that you guys are going to work with, just remember that fxy is always equal to fyx. So now that I've computed fxy, that's also going to be the same as fyx. So you're not going to need to like try to compute that one again later. You already have it. Okay. And then I was thinking of maybe skipping fy and fyy. Unless you guys want to see that, then I can certainly do that. Okay. But any questions about that problem? If not, I was thinking about going on to part 3, unless there's demand to see another problem from part 2. Okay. All right, so looks like there are no questions. So I will go ahead and take a look at part 3 next. Question 1 and part 3 has a typo in the answer. Okay, so we'll go ahead and work that one out. So that's the one that I was going to work on anyways. So I guess that works out nicely. And when we work it out, then maybe we'll see what the typo was at the end, all right? So part 3 was going over differentials a bit. And you might notice at the end when you're looking at the answers and the solutions, so you notice that for part 3, I kind of sketched a solution for the problem as opposed to like just giving the answer. Just because I felt like that was the type of question that I've seen lots of students have trouble with. So I wanted to try to give more of an indication of how to arrive at the answer at the end. But let's go ahead and work one of these out in some more detail. So we're going to do part 1, which is asking us to use the total differential to approximate the following number, the following expression. Okay. All right, so in this type of question, when you're asked to approximate something using the total differential, so I guess like the general formula for how you're going to approximate it, so you're going to approximate it as some function evaluated at some x and y, and then plus the total differential of that function. But in the problem, you are going to need to figure out what the function f is, and you're going to need to figure out what the x and the y are. And so you can do that by looking at the expression that you're trying to approximate. Before I do that, let me remind you guys about dz, which is what they refer to by the total differential. So remember that there was a formula for dz, which was the partial of f with respect to x times dx, and then plus the partial with respect to y times dy. Okay? All right. All right, so first regarding what is our function f going to be? So the idea is your function should resemble what you are trying to approximate. And looking at what we're trying to approximate, it seems to resemble the function f of xy is the square root of x squared minus y squared and plus 5, okay? All right, so first, do you guys kind of understand how we came up with that function based off the expression that we were trying to approximate? Okay. All right, so it looks like, okay, so before that, we are getting the partial derivatives to compute dz, so let me actually do that part first. Okay, so in order to get the partial derivatives, since we have a square root here, it'll be useful to think of it as being raised to a power of 1/2. Okay. So when I'm doing the derivative with respect to x, so there's going to be a chain rule involved. First things first is we're going to do the power rule, which for derivatives is to bring the exponent out front. And then decrease the exponent by 1. So 1/2 minus 1 is going to be negative 1/2. Right. But then there's a chain rule where we also need to multiply by the derivative of the inside. And here we're doing the derivative with respect to x. Okay. So the derivative of the inside with respect to x is going to be 2x. All right. And just simplifying, I can cancel the half with the 2. And then here with my negative 1/2 exponent, since it's negative, I'm going to move it to the denominator. And because it's a half, I'm going to rewrite it as a square root. Okay. That's going to give us fx first. And then fy is going to work very similarly. Okay, so to get the derivative with respect to y, you'll do the same thing at the beginning where you're just going to pull the exponent out front and decrease it by 1. Okay. All right, but then here, when we're doing the chain rule, where we need to multiply by the derivative of the inside, since we're doing it with respect to y, the derivative of the inside with respect to y is going to be negative 2y. And then when I'm simplifying this, I can again multiply the half with the 2 to cancel them out. But that leaves me with a negative y. And then for this term, again, I'm going to move it to the denominator because of the negative exponent. And because of the half, I'm going to rewrite it with a square root. All right, so that gets me all the partial derivatives that I need. Okay. All right, so next, in order to get our approximation, we need to figure out what x and y values we're going to plug into everything. And then we also need to figure out the values of dx and dy. So you can also figure out those just by looking at what you're trying to approximate. So here, I guess the idea is we have these complicated numbers, 6.02 and 3.99. So what I'm going to do, I'm just going to round them to the nearest nice number. So for 6.02, I'm going to round it to 6 because that's the nicest number that's close to it. And for the 3.99, I'm going to round it to 4 because that's the nicest number that's close to it. So these would be the values that I'm going to be plugging in for x and y everywhere. Now we also need to figure out what dx and dy were. So dx is the difference between what we had originally in our expression for x and what we ended up rounding it to. So in this case, dx will be 6.02 minus 6 should give me 0.02. And the same thing, dy is going to be, so take what you kind of originally had for y in your expression, and then minus what you ended up rounding it to. So here dy is going to be negative 0.01, okay? All right, so any questions on how I came up with the values for x and y, and how I got the values of dx and dy? Okay. All right, so What I want to do then is I want to plug in 6 and 4 for x and y. So I need to plug them into our original function f. And then also for the total differential, I'm also going to want to plug in 6 and 4 for x and y into fx and fy. And then also I need to multiply these by dx, which was 0.02 for this problem, and dy, which was negative 0.01. Okay. That will give us the value of dz, which then I would plug in over here. All right. So let me start by plugging in 6 and 4 into f and the partial derivatives. And give me 1 second, I gotta plug in my laptop. Okay. So I'll start by plugging in 6, 4 into my, all right. So if I plug in 6 for x, I'm gonna get 6 squared, which is 36. Minus, I'm gonna plug in 4 for y. So 4 squared is 16. And I'm gonna do plus 5. And then I'm square rooting all of it. Screen frozen again? Okay. I guess we're having some more technical issues than usual. So I'll just do what I did before. I'm gonna stop sharing, and now reshare. All right, good now? All right. Yeah, I've noticed recently I've been having a lot more technical difficulties with e-learning. And I'm not sure why that's the case, but that seems to be happening. So yeah, just keep letting me know if things like that happen. Hopefully it doesn't cause too many issues, all right? So here I get 20 plus 5 is 25. And square root of 25 gives us a final value of 5. Okay? All right, and then which part did you need me to explain? How I got, okay, all right, okay. All right, so let's see here. Okay, so I plugged 6.4 into my function. I also need to plug it into the partial derivatives for the total differential. All right, so plugging 6.4 into fx, we're going to have 6 in the numerator. And when I plug in 6 for x and 4 for y, we kind of already saw that it ends up being 5 in the end. Okay, so then fx is just going to be 6/5. And when I plug in 6 and 4 into fy, So we're going to get -4 in the numerator. And then again, we kind of already saw that for the square root in the denominator, that's all going to be 5 in the end. Okay? All right, so then finally, to get our approximation to this expression, okay, so the approximation, it should be f evaluated at 6,4. So that was equal to 5. That's going to be plus our total differential dz. And for dz, it was given by this formula that we had here. I'm going to go ahead and plug in 6/5 for my fx. And then it was times dx, which is 0.02. Okay, and let's see here. Fy was -4. I'm going to plug that in for Fy. And then it was times dy, which is -0.01. And then here you use a calculator to get what this is as a decimal. And let me see what that is. So I'll recalculate that because it looks like there might have been a mistake in my answer in the end. So maybe if there is a mistake in the calculation, I'll try to recalculate it real quickly. Okay, I don't think that worked. So let me try to calculate that again. Okay, so we'll have to write that down. Okay, so assuming I did that right with my calculator, it's 5 plus, and then everything here was equal to 0.025. So for my approximation, I'm going to get that this was approximately 5.025 in the end. Okay. Yeah, so it looks like I may have miscomputed it when I was doing it earlier. Okay. You got 0.016. Yeah, but someone got 0.32, which is actually what I had in the answer. So I guess we all need to be careful with how we're plugging it into our calculator in the end. Let's see here. Okay, it looks like the assuming that the answer that most people are getting is the right one, then it looks like the final answer should be the 5.032, which is actually what I had in my answer at the end of the practice problems that I sent to everyone, so I think that's good. All right, great. No, all right. I made a mistake too just now, so it's not a big deal. Okay, so any questions about that? If not, then I'll go ahead and see here. Yeah, so I'll proceed to part 4 then. Okay. And let's see here. So I think I'll do one problem from part 4, or well, I'll do one problem for part 4. I'll maybe do one problem for part 5. I might take a look at both problems for 5B, actually. Okay, all right. So let me do something for part 4 right now. After that, we'll take a quick little break, and then after that break, we'll look at parts 5A, 5B, and part 6, all right? But I'll go ahead and do a problem for part 4 right now. So part 5 was about finding local extrema or relative extrema and saddle points by using the second derivative test. All right. So let's quickly recall the second derivative test first. Okay, so so for the procedure for this type of problem is you first compute the first order partial derivatives, and you look for the critical points. And the critical points are where both fx and fy are equal to 0. Okay. So assuming we have a point x naught, y naught, that makes both of the first order partials equal to 0. So if we have this critical point here. So we want to determine if that critical point was a local minimum, a local maximum, or a saddle point. So to do that, you want to compute all of the second order partial derivatives. And then there is this expression, which I'm going to call d. So d is equal to fxx times fyy, then minus fxy all squared. And then what you'll do is you'll take your critical point and you're going to plug it into d, whatever the expression for d turns out to be. And so if d evaluated at your critical point is negative, then the second derivative test says that this critical point is a saddle point. Now, if when you plug your critical point into D, if it turns out to be positive, okay, then what you'll do is you'll go back and look at fxx, and if fxx at the critical point is also positive, then the function will have a local minimum at this critical point. But if D is positive, and then fxx turns out to be negative instead at the critical point, then your function will have a local max instead, okay? All right, so now I'm gonna do one problem from part 4, or one problem for part 4. But I'm thinking of doing something slightly different from what I have on my practice problems. So what I'm thinking of doing, so I'm guessing most of you want to see me do question number 3, is that correct? Like if I had to do only one problem from part 4, then you'd want me to do problem number 3. So I think what I'm gonna do instead, no, there's nothing wrong with problem number 3, but I think I'm gonna take a look at problem number 2, but to satisfy everyone, I'm going to add an E to problem number 2, okay? All right, so is everyone with me in what I'm doing? Yeah, so I decided I wanted to take a look at the second problem number 2, but I went ahead and added the E to it so that you could also see how it works when there's an E involved, okay? Okay, so first things first is we have to compute the first order partial derivatives and get the critical points. So we'll start by computing fx and fy. Now, if you guys remember the rule for getting derivatives of exponentials, so the rule is to just copy it down. And then you have to multiply by the derivative of the exponent. Here for fx, you'll want the derivative of the exponent with respect to x. Okay, so with respect to x, you're going to get 2xy plus 2x. Okay, so that's fx. For fy, so I'm going to, again, the rule is to copy down the exponential, so I'll do that first. And then again, you have to multiply by the derivative of the exponent. But this time we're doing it with respect to y. So that's going to give us x squared plus 4y and that should be it. Okay. All right. So then we want to set both of them equal to 0 because we're trying to find the critical points. All right. Now remember that exponentials, whatever you have in the exponent doesn't matter. But exponentials will never be equal to 0. So because the exponential can never equal 0, the only way for this product to equal 0 is for the first part to be 0. So I can just ignore the exponential right now and just take this first part and set it equal to 0. And the same thing for fy, just take the first part and just kind of ignore exponential. Okay. Okay, now solving for the critical points, that can be a little bit tricky. It really just depends on what you end up with when you take fx and fy and set it equal to 0. And so how you solve for the critical point, there's a couple different ways of doing it. For what I have right now, I noticed that in my first equation, I noticed that I can factor my first equation. So in particular, I see that there's a 2x common to both terms. So I'm going to factor out the 2x, which will leave me with y plus 1 equal to 0. And from there, that gives me two possibilities. So for this to be 0, either x is 0 or y could be negative 1. Okay. All right, so I'll get into like different cases then at this point. So first, let's consider if x is equal to 0. Okay. All right, so if x is equal to 0, then the first equation will be 0. But now I want to take a look at this over here next. And since x is equal to 0, I'm just going to plug in 0 for x. So that would just leave me with 4y is 0, which means that y must be equal to 0. And so that gets me the critical point 0, 0. Okay. All right, but then I have the second possibility, which is instead of x equals 0, it could also have been that y was negative 1 to make the first, to make fx equal to 0. So then if y is negative 1, then let's take a look at the second equation now. So I'm going to plug in negative 1 for y. So it'll tell me x squared minus 4 is equal to 0. Okay. And so maybe if we move the 4 over, and then when we square root, just remember that there's two solutions, plus and minus the square root of 4. So you get x could be plus or minus 2, okay? Okay, so then that gives us two critical points here. So x could be 2, with y being -1, or x could be -2, with y being -1, okay? So altogether, we ended up finding 3 critical points. All right, so now we'll need to test each of them to see if they're saddle, local min, or local max. And so to do that, I now need to compute all of my second order partial derivatives, okay? So that's going to be somewhat messy, but we can do it. Now, to get the second order partial derivatives, I'm going to need to do some product rules on this, because I have a product of like two functions. So let's remember what the product rule was real quickly. I'm going to write it out here. So UV prime, I remember it as U prime V plus UV prime, okay? So I need to apply it to getting fxx right now. Okay. So for fxx, that will be our u. The entire exponential is going to be our v. And I'm doing the derivatives with respect to x. Okay, so u prime, the derivative with respect to x right now, it's going to be 2y plus 2. Then it's going to be times v, so times the exponential. Oh, whoops. And just to save a little bit of time, I don't want to have to write all of this out. So I'm just going to start doing like random scribble, okay? But you should understand every time I write the squiggle, it's just supposed to be whatever is in the exponent, okay? All right, so that's my u prime times my v. And then next is going to be plus u. Okay, so u was the 2xy plus 2x. Now we need v prime. So I need the derivative of v with respect to x right now, because I'm doing fxx. Now, the derivative of the exponential with respect to x, incidentally, that was, we already computed it. So it's actually just going to be what we have for fx already. Okay. So then I'm just going to copy down what I have for fx. Okay. And then I'm going to simplify a little bit here. So what I'm going to do is I'm going to factor the exponential out from both of the terms. So that will leave me with the 2 plus 2 in here. And then I'm going to have these two multiplied together, which I can rewrite as 2xy plus 2x all squared, okay? All right, so any questions about fxx right now? right? So it seems like there aren't any questions. So let's take a look at, I'll do fxy next. Okay, so I'll go to fx, and I'm going to do the derivative of fx, but now with respect to y to get fxy. So it's another product. We're going to do u prime, which is now going to be u, but with respect to y. Okay, so that's going to be 2x for u with respect to y. So that's my u prime. And then I'm going to do times v, so times the exponential, and plus. And then next is going to be u. I'm just going to copy down what we had for u. And then it's going to be times v prime being the partial derivative of the exponential that we have here with respect to y. Now we already computed the partial derivative of the exponential with respect to y. That was just what we got for fy. So I'm just going to plug all of that in now. So copy down what fy was. And that's going to be our v prime, okay? Okay. Again, I'll simplify just a little bit here. I'm going to factor the exponential out again. So after factoring out the exponential, we're going to have 2x plus, and then here we've got 2xy plus 2x times x squared plus 4y, okay? All right, so any questions about fxy? Okay, so then finally, take a look at, we need fyy. Okay, so here's my fy up here. We're still going to do a product rule on it. So I have my u and my v. So for the product rule, u prime, that's going to be derivative of u with respect to y, which is just 4. So that's u prime times v, which will be the exponential. And then it's going to be plus u. So I'll copy down the x squared for y. And then times v prime, which will be v, but now with respect to y. And then again, the derivative of v with respect to y is just going to be fy. So I'm just going to copy what we found already for fy. And then again, I'm going to simplify a little bit by factoring my exponential out from both v with 4, and then plus, and then I'll write that as x squared plus 4y all squared, okay? So it took a bit of work, but now we finally found our fxx, fyy, and fxy, okay? So any questions about that before we apply the second derivative test to finish up the problem? Okay, all right. So see, I'm back to the test. Yeah, so I can take a look at that again. Okay, so when you take the partial derivatives and you set them equal to 0, you can just ignore the exponentials because exponentials are never 0. So just take these first parts and set them equal to 0 instead. And then from here, what I ended up doing was I saw that the first equation can be factored. I factored the 2x out from both terms. Then for this to be equal to 0, either x is 0 or y is -1. All right, do the little reset again. Okay. All right, so I know the exponentials. Take these first parts and set them equal to 0. And then for this particular example, you're able to factor one of the equations. So if you can factor one of your equations, go ahead and do that. Then we had, for this product to equal 0, either x had to be 0 or y had to be -1, okay? So I have two possibilities. So first I consider if x is 0. What I did was I plugged 0 in for x into the second equation now. And then from there, I was able to solve for y. And so we got that y is equal to 0. So that gave us 0, 0 for our xy critical point. Then I did kind of the same thing, but with y equals -1. So now I plug it into the second equation. So that becomes -4 once you plug in -1 for y. And then there's two solutions to this equation. X could be plus or minus 2. So then we had x was 2 and y was -1, or x was -2 and then y was -1, okay? And that's how we got the critical points. All right, so now what I'm gonna do is, let's see, let's write down what our critical points were. So we had 3 of them that we're gonna need to test. First one is 0, 0. Second one, 2, -1. And then third one was -2, -1, okay? All right. So I'm gonna need to plug all of them into fxx. Let's just write it all down. So fxx was 2y plus 2 plus the 2xy plus 2x times the exponential. Okay, so fxy. Okay, so that was 2x plus 2xy plus 2x times x squared plus 4y times the exponential. And then we'll need to compute f, y, which just for reference, I'll copy it down. Okay. And then we'll need d, which was fxx, times fyy, whoops, and minus fxy all squared. And then we'll be able to make our equation after all of that. Okay. So let's first plug in 0 for x and y. Okay, so in here, plugging in 0 for x and y will give you 2 times the exponential, which is actually not too important. So I'm just going to keep scribbles right now. Likewise, I'm just going to plug in 0 for x and y everywhere here. Well, I wrote it kind of weird, but that's okay. So plug in 0 for x and y. Notice that everything is just going to be 0. Here, if I plug in 0 for x and y, I'm just going to get 4 times the exponential still. So when I do d, so normally I put fyy next to fxx, but that was kind of my bad this time. All right, but I'm going to do fxx times fyy. That's going to be 8. And then we're going to have some exponentials, which are not too important. And I'm going to have minus fxy, which is 0 squared. Now remember that I said earlier that exponentials are never 0. But more precisely, exponentials are always positive, no matter what your exponent is. So without worrying too much what was in the exponent, we see that d is going to be positive altogether. So d was positive. So go back to fxx. It's also positive because exponential is always positive. Remember, if d is positive and if fxx is positive, then that means your function has a local min. So we have a local minimum at the point 0, 0 right now, okay? All right, so next let's plug in 2 and negative 1 into everything. So let's see, if I plug in negative 1 for y, we're going to get negative 2 plus 2. So those will actually cancel. Look here, if I plug in 2 for x and negative 1 for y, that's going to give me negative 4. And then 2 times 2 is 4. So actually, this term also becomes 0. So what I'm saying is every brackets was 0. So that's just going to be 0. All right, so now I'm going to plug in again 2 and negative 1 for x and y over here. So plug in 2 for x, I'm going to get 4 at the beginning. Let's see here. So plug in 2 for x and negative 1 for y. That's going to be negative 4 plus another 4. So the rest of it is just going to be 0. And then times the exponential. So ultimately, it's just 4 times e to some power. Okay, next, also plugging it into fyy. So we've got 4 plus. Okay, so here, if I plug in 2 for x, it's going to be 4. But negative 1 for y, so 4 minus 4 is 0. And then we have e to some power. So let's look at what we get for d. So when we do fxx times fyy, that's going to be 0 because fxx was 0. And then fxy was over here. So it's going to be minus 4 e to some power. Okay, so this part is positive. So the minus makes it negative. So if d is less than 0, then that means that we have a saddle point, okay? All right, so then finally, let's plug in negative 2 for x and negative 1 for y into everything. So if we plug in negative 1 for y, so again, we're going to get negative 2 plus 2, which will get 0 for that first part. Okay, over here, if we plug in negative 2 for x and negative 1 for y, that's going to give me 4. But then I'm going to get minus 4 when I plug in negative 2 for x. So actually, it's just all going to be 0 in the end. And then I'll just kind of go through the rest of it pretty quickly. That'll be negative 4, but the rest of it should become 0. So we're going to get an answer of negative 4 e to some power. For this one, if you check it closely, you'll get 4 plus 0, e to some power. All right, so when you're checking d, you're going to get 0 again for the first part because fxx was 0. Then you're going to get minus fxy was the, well, this time it's negative 4. But I kind of forgot should be squaring fxy. So because you're squaring, it's going to be positive, but then the minus in front makes it negative. So that means we get another saddle point here, okay? All right, and so then that would be it for that problem. All right, so do you guys have any questions about everything that I did just now? Yes. So then if there are no questions about that, we'll take a short break. Let's come back in 5 minutes, so around 3:05. And then we'll take a look at a couple more questions. We'll probably try to end at 4, okay? All right, so it has been about 5 minutes. So I'll go ahead and continue. All right, so I think for part 5, I think I'll just skip part 5A and we'll take a look at part 5B. All right, so both part 5A and 5B, we're covering the same things. It's just part 5B, you have some word problems instead. But both of them are going over Lagrange multiplier problems. All right, and so for these types of problems, the way they work is you're going to be given some function. And you're trying to find max or min of this function. And in the problem, there's going to be a constraint equation. So it seems that most people use g of xy for the constraint. So it'll be some function set equal to some constant. And so the way that Lagrange multiplier works is you'll need to compute the partial derivatives of f with respect to x and with respect to y. And then you'll need to do the same and compute the partial derivatives of g with respect to x, as well as g with respect to y. Now, once you have the partial derivatives, the method of Lagrange multiplier says that to find where your function has a max or a min, your fx should be equal to some multiple of gx, and that likewise fy should be equal to some multiple of gy. And this multiple here, and so this is a Greek letter, which is pronounced lambda. This is what they refer to as the Lagrange multiplier. Okay. Now for you guys though, you don't need to worry too much about this part though actually. So in the problems that you encounter, what you're able to do is if you divide these equations by each other, so namely if I take like fx and divide it by fy, and then if I, that would be equal to lambda gx over lambda gy. So the lambdas actually cancel if you do this. So then actually it doesn't really matter too much for us. And then usually what you want to do after you get to this point is you usually want to cross multiply. So then we do fx times gy. equal to fy times gx. Okay. And so for you guys, you don't really need to worry too much about all of this. And instead, you can pretty much, after computing the fx, fy, gx, and gy, you can pretty much jump straight to this and go from there, okay? So from these equations, what you'll do is you'll solve for some relation between x and y. And then after that, you're going to plug into your constraint equation. And from there, you should be able to solve for x and y, okay? So that's kind of a bird's eye view of the procedure. So first step is getting the partial derivatives. Second step is this. And then third step is that. It's kind of roughly speaking, okay? So we'll see how to apply that to some of our problems. So in part 5b, I'll take a look at problem number 2 right now. I think I'll also look at problem number 1 a little bit as well, but I think I want to start with problem number 2 first. So here we're given our function f of xy. So it's 10x to the 2/5, y to the 3/5. Okay. Some of you might enter this function later, I don't know, in some of your courses, but this is known as a Cobb-Douglas function. I guess it models a certain type of situation or problem in economics. I'm not too familiar with it, but if you're interested, you can look that up. Okay, so in the problem, F represents the total value of all goods produced. X and Y represent the amount of labor and capital needed for production. Okay, now, this next part is going to give us a constraint equation. So we're given a budget of $1,000. And we also have the cost per unit of labor and capital being $4 and $3. So then if the cost is $4 per unit of labor, and X represents the total amount of labor. And then if cost per unit of capital is $3, and Y represents the total amount of capital that we need, then this is going to tell us what the total cost was for all of the labor and capital that we use. And we have a budget of $1,000, so that has to be 1,000 and no more than that, okay? So we get our constraint equation from that second part. And then from here, once we have that, you can pretty much forget about the rest of the problem. You've got your function f, you've got your constraint, and now you can do the method of Lagrange multipliers. Okay. So the first step is to just compute all of the partial derivatives. So we're going to need fx first. So for fx, doing the partial with respect to x, so it's a power rule, so bring the 2/5 out front. Then decrease the exponent by 1. Okay. And then let's simplify that. So 20 over 5 is 4. And what I'm going to do is, since I have a negative exponent on the x, I'm going to move it to the denominator. So we're going to have y to the 3/5 over x to the 3/5. Okay. All right, and then similarly, we're going to compute fy. Okay, so now doing the partial with respect to y, so apply the power rule over here. We'll bring this out front, so it'll be 30 over 5. I'll copy down the x. Okay, and then we have to decrease the exponent by 1 here. So that's going to be y to the negative 2/5. If we simplify that, 30 over 5 is 6. And then likewise here, I got the negative exponent, so I'm going to move it to the denominator. So that gets us our fy, okay? All right, so then we'll compute gx and gy as well. So this would be our g of xy. So partial with respect to x will just be 4. And partial with respect to y would just be 3, okay? So once we get all the first order partial derivatives, so remember for the next part, we're going to sort of cross multiply and then set them equal to each other. So when I multiply fx with gy, I'm going to get a total of 12. And then we have y to the 3/5 over x to the 3/5. Likewise, we're going to cross multiply here, so it's going to be 24. And then you're going to get x to the 2/5 over y to the 2/5. Okay. And what we want to do now is manipulate this equation and try to get some relation between x and y. So the best thing to do right now is to actually sort of cross multiply again. So multiply the y to the 2/5 over to here, and the x to the 3/5 over to here, okay? So when we do y to the 3/5 times y to the 2/5, that's just going to be 12y. And then likewise over here, if I multiply x to the 3/5 with x to the 2/5, that's just going to be x. And here we may as well divide by 12, so we get y equals 2x, okay? So now that's the relationship between x and y that we solved for. So then once we find that relationship between x and y, we're going to go back to our constraint equation. So the constraint equation was 4x plus 3y equals 1,000. And I'm just going to plug this in now. So I'm going to replace y with 2x. Okay. From there, we get 4x plus 6x for a total of 10x. And from there, we're able to solve for x. So x is going to be 1,000 over 10, which is 100. And then x is 100. Then from this relationship that we found earlier, we said that y would be 2 times 100, so y would be 200, okay? So then this would give us the optimal combination of labor and capital that we would need in order to maximize the total value of production. So we would need 100 units labor and 200 units of capital, okay? All right, so any questions about that? All right. So I think I'll go ahead and take a look at problem 1 from B as well. I at least want to help you guys set it up, like what was your F, what was your constraint equation, okay? Okay, so we're trying to build a rectangular fence. So I'm going to draw a rectangular fence right now. And here it says that there's going to be additional fencing across the middle. So I'm going to add some additional fencing just across the middle like that. Okay. So it tells us we have 65 meters of fencing available. So that's going to contribute to our constraint equation. And then here we're trying to find the maximum possible area. Okay. So what I'm going to do is I'm going to add some variables into my picture. So let's say that x represents this total distance. And let's say y represents that length or distance, okay? All right, so given x and y representing these dimensions for the fence, so the area, remember that the area of a rectangle was like the base times height or length times width, where you want to think about it. So in this case, then area would simply be x times y. And since we're trying to maximize the area of this fence, remember that what you're trying to maximize or minimize, that represents the function f. Okay. So we're going to be using f of xy equals xy because of that. And then for the constraint equation, okay, so the constraint is that we have 65 meters of fencing available. So in terms of x and y, if we think about how much fencing we're using, so we're using, for these two sides of the fence, we're using a total of 2x amount of fencing for like the bottom and the top here. In addition to that 2x amount of fencing that we're using, we're also using 3y amount of fencing for the left and the right, and this like additional fencing that we had in the middle. So 3 y's altogether. So that would be the total amount of fencing that we are using. And we only have 65 meters of fencing available. So this would have to be 65, okay? So then once you identify your f of xy in your constraint equation, you can then go through the procedure of getting the, computing the partial derivatives, doing the whole cross multiplication thing and whatnot, okay? But I think maybe since I will have some time to do some problems in part 6, I think I won't work through the rest of the problem. But here you can at least see how to read the problem and how to get your f and your constraint from it. All right, so any questions about that? All right, so let's take a look at part 6 then. Which is just going to be evaluating a few integrals. So I think let's take a look at problem number 2 first from part 6. So we've got this double integral. The function that we have is 2e to the 2x minus 3y. And we're doing the double integral over the region R. And here you see that R was defined with x being between 0 and 1, y being between 0 and x. So that there is telling you what the bounds on the integrals are going to be. So on the inside, we're integrating with respect to y. So bounds on y were given to be 0 to x. And then for the outside, for integrating with respect to x, we were given bounds of 0 to 1. Okay? All right. So now we're trying to evaluate the double integral. So you start with whatever was inside first. So let's just focus on this integral right now, 0 to x of e to the 2x minus 3y dy. So since we are treating, we're integrating with respect to y, so we're going to treat x as if it were a constant over here, okay? All right. Now, so then we're trying to integrate an exponential. And in the exponent, we have something that looks like this, where a and b are just constants. Okay. And so that's because since we're integrating with respect to y, we are treating 2x as if it were a constant. Okay. All right, so when you have something like this and you're finding the integral, so the rule is to divide by the coefficient of x. So it's going to be 1 over b. And then it'll be times the exponential. Okay? All right, so I'm going to apply that rule to what we have right now. Okay, so since y is our variable, since we're integrating with respect to y, so the coefficient of y was -3. So I'm going to do -1/3, and then times the exponential. So that's the integral, and now we're going to plug in 0 and x. All right, so first when we plug in x, and we're plugging into y, because we were integrating with respect to y. So we're going to get -1/3 to 2x minus 3x. Okay, plug in x for y. Minus what you get when you plug in 0 for y, which will leave us with e to the 2x there, okay? So then altogether, we're going to get -1/3. 2x minus 3x leaves us with -1x in the exponent. And then here we're going to get plus 1/3 e to the 2x. Okay? All right, so any questions about that part so far? Okay. All right, so then that was just the inside though, so we still have the integral on the outside. Okay, so in the inside we got -1/3 e to the -x plus 1/3 e to the 2x. And so finally just integrating this. So to integrate e to the -x, so we'll divide by -1 to make it positive, and then copy down the exponential. For this one, we're going to divide by 2, so it's going to be 1/6, and then e to the 2x again. We're going to plug in 0 and 1. Yeah, so you could have approached the problem by doing U substitution. So if you did U substitution, you would have ended up applying this rule that I wrote down basically. So like this rule comes from doing U substitution. But I feel like this is a rule that's just good to know off the top of your head. So that when you see a situation like this, that you'll be able to just like write down the integral without doing the U substitution, okay? It's just like before how when we covered the integral of e to the kx, and I just gave you guys like the formula is this. So like this actually comes from U substitution. But it's like good to know it off the top of your head so that you won't have to do U sub every time you see it, okay? Okay, all right. And then here, just finish up. So we're going to plug in 1 for x. All right. And then we're going to minus what we get when we plug in 0 for x. So remember, e to the 0 is 1. So you're going to get that at the end, okay? And there's not much you can do to simplify. Can't really do anything with this first part. Don't know if you'd really need to simplify, but if you were to, 1/3 is 2/6, and then 2/6 plus 1/6 is 3/6, which would then be 1/2, okay? Okay, so then, let's see here. Okay. All right, so then let's look at question number 3, and then we'll look at 4 and 5 as well. Okay, so 3, it says to calculate volume underneath the surface, and they give you z equals xy. Okay, so when they give you z equals a function of x and y, that's basically the function that you're going to be integrating. Okay, so I'll already go ahead and put xy into my double integral. So we want the volume underneath the surface, and then it's above this region. So it's given that y is between 0 and then the square root of 1 minus x squared. So I'm going to put that on the inside. So that would be integrating with respect to y. And then that leaves the integral with x between 0 and 1 with respect to x on the outside, okay? All right. So that's how you would set up the problem. And then this, when you evaluate this double integral, then it's going to give you the volume that the question was asking for, okay? I'll make a small note right now that when you're setting up a double integral, okay, so the bounds on the outer integral should always just be numbers. So there should be no x's or y's in it. As you've seen the bounds on the inside, it could have some variables in it, an x or a y perhaps. Okay. So the reason why I ended up setting my integrals up in this way, because the variable bounds have to be on the inside, that's how I knew to put this part on the inside first. And then since these are bounds on y, that's why we're adding with respect to y. And then that lets us with the bounds on x for the outside with respect to x, okay? And this one's not too bad, so I'll go ahead and work through the problem. Okay. So on the inside, we're treating x as a constant and just integrating y. So we're just going to get y squared over 2. And then we need to plug in 0 and 1 minus x squared for y, okay? Okay, so we'll plug the square root in for y. And then when we plug in 0 for y, it's just going to be 0. And then here it's nice because when you square the square root, they just cancel out. So now it's just going to be x times 1 minus x squared all over 2. Not a big deal, but maybe I'll pull out the 1/2 here. And then just distribute the x now. And then from there, you're able to evaluate the integral, okay? So that'll be x squared over 2 minus x to the 4th power over 4, x squared over 2 minus x to the 4th over 4, and then plugging in 0 and 1. And I guess when you plug in 1, it'll be 1/2 minus 1/4. And you'll get 0 when you plug in 0, okay? 1/2 minus 1/4 is 1/4. So 1/2 times 1/4 will give us an 1/8 at the end. Okay? All right, any questions about that one? All right. So we'll take a look at number 4 next. So 4 and 5 are a little bit different. All right, so we're given this double integral right now. And the instructions are to sketch the region of integration and then to switch the order of integration, okay? So we're going to rewrite this integral so that we'd be integrating with respect to y on the inside and then x on the outside, okay? So from dx dy to now dy dx. Okay, so that's what we mean by trying to switch the order of integration. Now, when we do that, we have to be a little bit careful about how the bounds are affected when we try to switch the order. And so I guess like the best way to figure out what your new bounds are going to be, the best way to do that is to look at a sketch of the region of integration. Okay. So the region of integration we can get from our bounds over here right now. So here the 0 and 9, those are bounds on y because they're the outer integral. So we've got y's between 0 and 9. And then here, these are bounds on x for the inside integral. So we've got x between 0 and root y. Okay. So we want to try to sketch this in a picture. So I'm going to start with y being between 0 and 9, which let's just say is somewhere up here. So x starts at 0. Okay, so x equals 0. That's going to be everything along the y-axis. And then we've got bounded above by the square root of y. So when you look at what x equals square root of y would be, if you square both sides, it'll look more familiar to you. It'll be y equals x squared. And you know that y equals x squared is just a parabola. So what I'm going to do is I'm going to draw the parabola, something like that. Okay. All right. And so since we had x was bounded below by 0, which was the y-axis, and then it's bounded above by the parabola. And then y is bounded between 0, which is down here. This is y equals 0. Y equals 9 was up here. Okay. So we see that the region of integration is going to be this region over here, okay? All right. So once we see what the region of integration looks like, now I want to find what the bounds should be if I do y on the inside and x on the outside. So the way that I like to do this is I like to start with the outside integral. Okay. So remember that the bounds on the outside should be just numbers, okay? So if I want bounds on x in this region, I would say that starts at 0. And the furthest out that x will go is here, okay? And if I want to know what x value this is going to be, so when y is equal to 9, if I think about what x would be for the parabola, so when y is 9, x should be the square root of 9, and square root of 9 is 3, okay? So altogether, x will range from 0 to 3. And I'm going to use that for my bounds on the outside with respect to x, okay? And then for the bounds on the inside, so we have that y is bounded below by the parabola. So the parabola is y equals x squared. So we're going to say the lower bound on y is x squared. And then y is bounded above by 9. So give me the upper bound for y, okay? Okay, so I'll talk a little bit more about how that works right now. Probably most of you are able to follow that, but if you're still a little bit iffy, I'll try to explain a little bit more exactly how this is working. So we had x ranging from 0 to 3 altogether. So that gave us the bounds on x on the outside. So a good way to think about the inner integral, so we're integrating with respect to y. And remember that when you're integrating with respect to y, that you're going to treat x as a constant. So a good way to think about this is if we take some x value between 0 and 3, and we just hold it constant, okay? So imagine we just have this single fixed constant value of x right now. So what would the bounds on y be when you hold x to be constant? Okay. So here we see that, okay. for this constant value of x, the smallest value of y is going to be over here. And since this was the parabola y equals x squared, so if this is x, then we know the y coordinate would be x squared. And then what would the upper bound on y be when we're holding this constant value of x? So it starts at x squared and it still goes up to 9 altogether. And that's how you can see the bounds for y being x squared to 9 on the inside, okay? And for every x between 0 and 3, you'll get the same lower bound of x squared for y and the same upper bound for 9. And so that's kind of the idea of why the bounds on the inside were x squared to 9, okay? All right, so any questions about that? All right, great. Thank you. All right, so I think we can go ahead and just do the last problem, and then we'll wrap it up there, okay? Because here's number 5. We have the integral from 1 to 3, and then 1 to 2x minus 1. So notice I didn't bother to give you guys a specific function. So because you don't have an actual function here, you're just switching the order and you're not actually carrying out the integration afterwards. So the main purpose was just getting you guys to know how to switch the order of integration. The other thing that I think I wanted to try to emphasize is that when you're getting the region of integration, that it only depends on the bounds in your integral, and that whatever function you had that you were trying to integrate, it has no real relation to the region of integration. Okay. So for this problem, the bounds on x on the outside were 1 and 3. And then the bounds on y on the inside, 1 and 2x minus 1. Okay, so let's mark x equals 1 and x3 first. So that's where x is 1 and 3. And then we have y begins at 1. And then for the upper bound on y, so we've got 2x minus 1. All right, so that this is the equation of a line. Okay. All right, so let's see, when x is 1, you'll just get that y equals 1. So we are starting at this point where x is 1 and y is 1. And then I'm just going to check x is 3. Okay. Plug in 3 for x, you're going to get 6 minus 1, so we'll get y is 5. All right, so the line starts at 1, 1 and goes up to 3, 5. So it's going to look like this. Okay? And so y is bounded below by y equals 1, and then above by this line. X starts at 1 and goes up to 3. So this triangle is going to be the region of integration, okay? All right, so now to get the bounds when I switch the order of integration, so I'm going to start with the outside. So for bounds on y, we're just going to have y ranges from 1 to 5 altogether. So again, remember for the outside, the bounds should just be the numbers. So we're just going to have 1 to 5 for y. All right, now for x, so inside the region, x is bounded below by this line, and then it'll be bounded above by 3. So I'll go ahead and put in 3 for the upper bound on x. And then as for the lower bound being this line, so I know that the equation of the line was y equals 2x minus 1. All right, but to get the bounds for x, I need to solve for x to write it like x equals something. So we'll add 1 to the other side and then divide by 2. Okay? And then that's the equation of the line, but like for x in terms of x. So that would be the lower bound for x over here. Okay? And that would be it for switching the order of integration. And then just real quickly for a better explanation of that. So the idea is y ranges from 1 to 5. And then on the inside integral, if you take a value of y between 1 and 5 and hold it constant, and then you see what would the bounds of x be when you hold a value of constant. So it goes up to 3 for x, and then it starts here for the lower bound on x. And you would calculate this value by using the equation of your line. So it would have been half y plus 1 here. And that's why the bounds of the integral are from here to here, okay? All right, so any questions about that?